Hello everyone, this is Sandeep Sir here. In this video, we are going to discuss one of the very important topics, that is semiconductor electronics. So let's start. First, when we talk about semiconductor, okay, what is a semiconductor? It is a solid having conductivity between that of the conductor and insulator. Yes or no? So we know that conductors are having very high conductivity, whereas resistivity of conductor is less. Okay, insulators their conductivity is very less, but resistivity is very high. In case of semiconductor, the conductivity lies between metals and non-metals. Okay, so to understand these concepts, first few important terms are there that you should know. Energy band, the group of closely packed energy levels is called as energy band. Okay, what happens in case of an atom? An atom contains nucleus in the center, yes or no, and electrons are revolving around the nucleus in circular path, that is called as cell or orbit, yes or no. So that if a group of closely packed energy levels are called as energy bands. Now we have actually electrons will be available in the cell, right? Because of the repulsion, in first shell there are 2 electrons, next shell there are 8 electrons, yes or no. Because of heavy repulsor between the electrons, these energy levels will break into energy bands. Energy levels are there, it will break into energy bands. So 2 type of energy band is generated. Okay, so one is what a valence band and other is what a conduction band. Valence band and conduction band. This band formation takes place due to the heavy repulsion between the electrons present in the energy levels, yes or no. So 2 types of bands are there, one is a valence band, other is conduction band. Okay, valence band, the energy band which are completely filled at 0 Kelvin are called as valence band. Okay, whereas conduction band, the energy band above the valence band is called a conduction band. It may be empty or it may be partially filled. So now, what do you mean by energy gap? The gap between the valence band and the conduction band is called as energy gap. Now they may ask you one question, okay, 3 to 5 marks on the basis of energy band diagram, distinguish between conductors, insulators and semiconductors. So try to understand these concepts. In case of conductors, the 2 bands, that is the conduction band and the valence band are overlapped. So energy gap is 0. Okay, here in case of conductor, conductivity is very high. Okay, that is 10 to power plus 2 to 10 to power plus 8 Siemens per meter, whereas resistivity is very low, 10 to power minus 2 to 10 to power minus 8 ohm meter. Okay, when we talk about semiconductor, in case of semiconductor, okay, there is a small energy gap between the conduction band and the valence band. It is generally less than 3 electron volt. Okay, here energy gap is less than 3 electron volt. Conductivity is intermediate between conductor and insulator, that is 10 to power plus 5 to 10 to power minus 6 Siemens per meter, whereas when we talk about the resistivity, so it will be intermediate between the conductor and insulator. So just take the reciprocal, it becomes 10 to power minus 5 to 10 to power plus 6. Okay, ohm meter. This is what a ohm meter. Okay, let's talk about the insulator. In case of insulator, there is a huge energy gap between the conduction band and the valence band. It is generally more than 3 electron volt. It may be 6 electron volt. Okay, 7 electron volt. So generally energy gap is greater than 3 electron volt. So electron which are present in the valence band, okay, so it cannot reach to the conduction band. That's why it will never conduct. For example, in case of non-metals, okay, carbon, okay, nitrogen, oxygen, all the non-metals are example of conductors. When we talk about the examples of conductor, all metals generally, okay, sodium, potassium, calcium, magnesium, iron. Okay, here you can write iron example, copper, silver. Semiconductor example, you should remember silicon, germanium. Okay, group of 14 elements of the periodic table. Insulators, most of the non-metals like carbon, nitrogen, oxygen, fluorine. Okay, so they are insulator. In case of insulator, the conductivity is very less, 10 to power minus 11 to 10 power minus 19 Siemens per meter, whereas resistivity, okay, rho is very high. This is what a 10 to the power plus 11 to 10 to the power plus 19 ohm meter. Is it clear? Now let's start, let's discuss about the, here also you can see in this diagram, okay, energy gap is there. In case of semiconductor, okay, it is approximately, they have shown and approximately 1 electron volt, like in case of silicon, germanium, okay, and in case of conduct metals, energy gap is 0, the two bands are overlapped, okay. In case of insulator like non-metals, there is a huge energy gap, okay, 6 electron volt they have shown, yes or no, okay. In case of semiconductor, it is less than approximately 1 electron volt they have shown, okay, now fine. Next, semiconductor is of generally two types, one is intrinsic, other is extrinsic. Intrinsic semiconductors are the pure semiconductor, okay. Let's discuss first intrinsic semiconductor, that is silicon, okay. When we talk about silicon, atomic number of silicon is 14, okay, electronic configuration 2, 8, 4, yes or no. Now try to understand that silicon is having 4 valence electron, okay, silicon is having 4 valence electron, yes or no. Now to become stable, what it will do, the silicon atoms will share the 4 electrons from other atoms, okay, near atoms, neighboring atoms, and it becomes stable, yes or no. So I am just showing a stability for one atom. Suppose this silicon atom, you see it is having 4 valence electron, so it will take one from here, one from here, one from here, and one from here, like that it will become stable. Similarly, each silicon atoms will share 1 electrons and become stable. So you can see in this diagram, okay, silicon is sharing 1 electron from the each neighboring atom and it is becoming stable. This is a pure semiconductor, okay, silicon, pure germanium, they are what, intrinsic semiconductor. In this case, number of electrons and number of holes are same. Conductivity of pure or intrinsic semiconductor is what, less. To increase the conductivity of this semiconductor, we are doping with some impure atoms, okay. The process of adding impure atom is called as doping. So we are doping with trivalent atoms and pentavalent atoms. So we will discuss here, when we talk about the pure semiconductor, group 14 elements, okay, carbon, silicon, germanium, group 14 elements of the periodic table. So generally silicon, germanium, they are what, semiconductor. So they are tetravalent. Why? Because valence electron is 4, that's why they are tetravalent. Is it clear? Okay. Next, we talk about extrinsic semiconductor, okay, that is a p type first. In the p type, we are doping with a trivalent atoms, okay, trivalent atoms like group 13 elements, aluminum, okay. When we talk about aluminum, you see aluminum 2, 8, 3, okay. So these are trivalent atoms. So when you dope with millions of trivalent atoms, so millions of holes are generated and each hole is treated as positive charge. In this way, the p type of semiconductor is formed, okay. N type, here in this case we are doping with pentavalent atoms like phosphorus, okay, whose atomic number is what, 15. So 2, 8, 5, so valence electron is 5, yes or no. So what happens, N type in the case of N type semiconductor, when we dope with pentavalent atoms, so 4 electrons it will share and 1 extra electrons will be present in the interstitial lattice. So extra electrons, if you will be there, if you dope with millions of pentavalent atoms, you will get millions of extra electrons. So the charge carriers are increased, okay. That's why conductivity of N type is high. Same with the p type. Here we can see in the details, okay, p type semiconductor. When a pure semiconductor is doped with a trivalent impurities like group 13 elements, as I told you, boron, aluminum, indium, gallium, then the 3 valence electrons of the impurity bond with 3 of the 4 valence electrons of the semiconductors, okay. This leaves an absence of electron, that is hole in the impurity. You can see germanium is there. Suppose we are doping with here, let's take aluminum. Suppose we are doping with aluminum. So aluminum is giving 1 electron here, 1 electron here, 1 electron here, and here hole is generated, yes or no, and hole is treated as positive charge, that's why p type of semiconductor is formed. Okay, so with increase in the number of impurities, that is holes, the impurities holes, the positive charge carriers are increased, hence it is called as p type semiconductor. Okay, now next, when we talk about n type semiconductor, n type semiconductor, you can see when a pure semiconductor, that is silicon or germanium, is doped by pentavalent impurities like phosphorus, arsenic, antimony or bismuth, then 4 electrons of the 5 valence electrons bonds with 4 electrons of the germanium or silicon, and the 5th electrons of the dopant is set free. You can see here, these are the silicons. Okay, silicons are there, and we are doping with antimony, Sb. Sb is having 5 valence electrons. It is giving 1 here, 1 here, 1 here, 1 here, and 1 electrons will come to the interstitial lattice, that is the free electrons. This is the free electrons. Okay, that is treated as negative charge. That's why it is called as n type semiconductor. So here we can say that in n type, number of electrons is far more than the number of holes. Okay, whereas in case of p type, number of holes, okay, you can remember number of holes is far more than number of electrons. So conductivity is mainly due to the movement of holes. You can see this is the hole. Yes or no? Okay, so in case of intrinsic, number of holes and number of electrons are equal, NH is equal to Ne. In case of extrinsics, that also p type and n type. In p type, number of holes is far more than number of electrons. In case of n type, number of electrons is far more than the number of holes. Yes or no? So we can see. Okay, you can go through the points which we discussed. You can take the screenshot. Metals conductivity, as already discussed in the beginning. Okay, conductivity range and resistivity range for metals which are conductors, insulators and semiconductors is there. Okay, now let's talk about the PN junction diode. Okay, and we will discuss about very important topic, that is rectifier. Okay, half wave rectifier and full wave rectifier. First we will see the PN junction diode. What happens whenever p type of semiconductor is fused with n type of semiconductor? Okay, so let's take a p type is there, p type semiconductor and n type semiconductor is fused. So what happens near the junction? Okay, near the junction, they have the holes are the majority charge carrier. Yes or no? Here we can say that electrons are the majority charge carriers. Near the junctions, the holes and electrons which are oppositely charged will fuse together. Okay, now so holes will move here, electrons will come here. Okay, holes will move here, electrons will come here. Yes or no? So one region is developed, that is called as depletion region, so that further holes is not able to move this side and further electrons is not able to move this side. Okay, because one potential is developed, that is called as barrier potential. Barrier potential. Okay, so holes are the majority charge carriers carrying on p sides and electrons on the n sides, or hole diffused to the n side and electrons to the p side. Yes or no? So depletion region, the junction region has very low density of either p or n type carriers because of the interfusion will happen here. Yes or no? So we talk about the forward bias and reverse bias now. What do you mean by forward bias and reverse bias? When p side is connected to the positive and n side is connected to the negative, then in this case it is called as forward bias. Okay, what will happen? Try to understand. Here holes are the majority charge carriers. Yes or no? Here electrons are the majority charge carrier. Okay, here electrons are the majority charge carriers. So what will happen? This end become positive. Why? Because this is positive means this side become positive. Okay, this is negative of that battery means this side become negative. Yes or no? So when here holes will be there, so like charges we know that repel each other, so holes will move in this direction. Yes or no? All the holes will move in this direction. What about the electrons? Electrons are the negatively charged particle. Yes or no? So as it is negatively charged particle, so it will be also repelled in this direction. So our all holes are moving in this direction, so current will be also in the same direction. Current will be also in the same direction. As electrons are moving in this side, so current will be in the opposite side. So overall current flows from P to N. Current flows from P to N. In this case, what happens? The diode conducts. Diode acts as a closed switch. Diode acts as a closed switch. And diode conducts. Diode conducts. Okay. Now when we talk about the reverse bias. Okay. When P is connected to the negative and N is connected to the positive, it is called as what? A reverse bias. Now what happens as it is negative? So here this end become negative. So you can see here holes are here. Okay, so holes will move which direction? Towards the negative charge, yes or no? So all the holes will move. So width of depletion region will increase, yes or no? Here as it is a positive here, so this end become positive, correct? Now what happens here? Electrons are the majority charge carrier. What happened to the electrons? It will move in this side, towards this side. So electrons current will be which direction? In this direction. Okay, actually there is no proper orientation or movement of electrons and holes, yes or no? So here width of depletion region increased here, as the holes are moving here and electrons are moving here, so width of depletion region decreases. Here it will keep on increasing. In this case what happens? The diode act as a open switch, and it will not conduct. It does not conduct. These two concepts you should remember. Okay, now let's talk about the VI characteristics. What happens? Okay, this is the forward bias condition, this is the forward current. We are supplying the voltage. Okay, let's take a forward bias. So P is there, N is there. So here P is connected to the positive, N is connected to the negative. Okay, so if you give a 0.1 volt, 0.2 volt, 0.3 volt, 0.4 volt, up to that what happens? The holes are not able to cross the barrier potential depletion region, yes or no? So there will be no flow of current, okay, which is observed here. Now as soon as it reaches the barrier potential, which is generally 0.7, okay, electron volt, okay, it is there for silicon 0.7 volt. So as this is volt only, 0.7 volt for silicon, okay, 0.7 volt. As soon as you give 0.7 volt, so all the holes will start moving and electrons will start moving. So current will, in the beginning there will be no current, current will suddenly increase, yes or no? So that particular voltage at which the current suddenly rises, that is called as what? A knee voltage or cutoff voltage in the forward bias condition, yes or no? So they may ask you the definition of knee voltage. Okay. Next, we talk about the half wave rectifier, which is very, very important. Half wave rectifier and full wave rectifier. These questions may be asked for 5 marks. Okay, half wave rectifier and full wave rectifier. So first, let's see half wave rectifier. Here you can see forward bias and reverse bias nodes are there. Okay, what happens in case of forward bias? You can take the screenshot. Okay. In case of forward bias, P is connected to the positive and N is connected to the negative. Okay, forward bias. Okay, reverse bias, when P is connected to the negative and N side is connected to the positive, it is called as reverse bias. You can go through. Okay, now okay, bridge rectifier is not there in syllabus. What is rectifier? First you try to understand. When we talk about rectifier, a rectifier is actually a device which converts AC to DC. Okay, what do you mean by rectifier? Rectifier is a device which converts AC to DC. So you need to understand what is AC and what is DC. Okay, AC is alternating current. Okay, it flows in both that cycle. Okay, this is IAC. So no, correct? IDC means what? It will, okay, IDC. It will flow in one direction only, IDC. Yes or no? Even this is also with time IDC. Okay, this is a direct current which is flowing in one direction only. But alternating current flows in both cycle, plus minus. Yes or no? Correct or not? So what is rectifier doing? The rectifier will convert AC to DC. Okay, so here the construction is like this. This is the primary circuit. Okay, this is the primary circuit. Coils are there. Yes or no? This is the primary coil. And this is a secondary coil. okay, and here diode is there, and then load resistor R is connected. Yes or no? We'll get the output across this. Now try to understand. We are giving the input like this. Okay, this is the IAC. See, let's say this is A, this is B. Okay, let's say this is C and this is D. Okay, during the positive half cycle, try to understand. During the positive half cycle, okay, here positive is induced due to mutual induction. This is a primary coil and secondary coil. They are mutually coupled with each other. So during the positive half cycle, what happens? Positive is induced at point A, and when P is connected to the positive, it will be forward bias. The diode will conduct, so current will start flowing through this end. What will happen? Negative will be there, so negative and positive. Here current is flowing, so we will get the output. We'll get the output during the positive half cycle. Okay, what will happen during the negative half cycle? Right now, see, during the negative half cycle, here during the negative half cycle, okay, what happens? Here negative is induced. When P is connected to the negative, it is reverse bias. In case of reverse bias, it will act as an open switch. Okay, now so diode will not conduct, so we will not get the output during the negative half cycle. Again, during positive half cycle, we will get the output, and during the negative half cycle, we will not get the output. So only one half of the input signal is rectified. That's why it is called as half wave rectifier. Is it clear? So you can see the explanation. Okay, during positive half cycle, the terminal A will be positive. Here you can see this is the terminal A, you can assume. Okay, will be at a positive potential and B will be at a negative potential. So it will make a diode D in the forward bias and it will act as a short circuit. Okay, yes or no? So we will get the output during the positive half cycle. During the negative half cycle, you see the terminal A will be at a, during negative half cycle, what happens? Terminal A will become negative. Yes or no? Don't change the diode, actually here they have changed. So try to, here only you try to understand. Okay, during negative half cycle, okay, here negative is induced, so diode when P is connected to negative, it is reverse bias. Okay, so diode will not conduct, it will act as an open switch. So terminal A will be at negative potential and terminal B will be at a positive potential. Okay, here positive will be there at the same time. So it will make a diode reverse bias and diode act as a open switch or open circuit. Okay, now in this way the current flows through load resistors in only one direction. Yes or no? Is it clear? So this is the graph. Input is like this AC and output is DC. Okay. Okay. This is a bridge rectifier which is not there in your syllabus. Now coming to the full wave rectifier. Okay. When we talk about the full wave rectifier, so here we are using two diode. Okay. How many diodes are used? Two diodes are used. Okay. Let's see here. Okay, this is diode 1, diode 2 is used, and we are giving this the primary coil, this is the secondary coil. Okay, so let's take a B, C and D. Okay, so during the positive half cycle, you try to understand here what happens. Positive is induced here. Okay, at the same time negative will go here. When diode D1 is connected to positive, it is forward bias. Diode D1 is forward bias, whereas diode D2 is connected. Here we will get a negative, so it will be reverse bias first case. So diode D1 will conduct here. This is a center typing. Okay, yes or no, to complete the circuit. So during the positive half cycle only. Okay, this is the cycle I am showing. AC is the input we are giving, IAC. Let's see output. So during the positive half cycle we are getting the output. Okay, output is there due to diode current 1 into load resistance RL. This is the load resistor. Okay, R1 they have taken. Okay, R1 you take, no problem. Okay, now during the negative half cycle you see here. Okay, so during the negative half cycle what is going to happen? During the negative half cycle you will get negative is going this side, so negative is induced here. Okay, at the same time positive is going here, so positive is induced here. Now you can see diode D1. Okay, P is connected to the negative, so it is what? A reverse biased, so it will not conduct. Whereas here this side is positive, so when diode D2 is connected to positive, it will be forward bias, so it will conduct. So current will go through this like this and it will move. So we will get the output okay, due to diode current D2, diode current 2. Okay, now so here this is the center tap to complete the path. So here current will go like this, we will get the output across this. So here we'll get the output due to diode D2. First case diode D1. As both half of the input signal is rectified, that's why it is called as full wave rectifier. Full wave rectifier. Is it clear? So it's all about a rectifier. Okay, N type, P type, intrinsic and extrinsic, forward bias and reverse bias. I hope you understood these concepts. Please share with your friends, subscribe the channel. Thank you.